All right. Hello, everyone. My name is Engin Kayraklioglu. I'm the GPU lead of the Chapel team at Hewlett Packard Enterprise, and this is my second live demo that I'll be giving on GPU Sport. If you missed the first one, I recommend checking out Chapel's YouTube channel, where there is a playlist of demos somewhere here. If you go to Chapel demo sessions, you will see a playlist with all the demos that we have done, and one of them is Introduction to GPU Programming in Chapel. So that was the first demo that I made a while ago. And what happened after that is I also created this repo with example codes from that first demo, which was covering very basics and basically introduction to fundamental concepts of Chapel and then some basic GPU operations. So definitely feel free to check this repo on GitHub. And what I will do today is I will work on this repo and hopefully add more examples to it. But before I do that, I will just go through these examples in a very quick pace. So there might be things that are missing in my explanation. So definitely feel free to reach out or check out the previous recording of the demo. All right, so here I'm on my terminal. I will show the code on the left-hand side, and the right-hand side will be where I compile. And this is not my typical work setup, so there will be some hiccups, I'm pretty sure, along the way, so please bear with me with that. So again, on the left-hand side, we are seeing the code that we have. So this was my introductory example from that initial demo, and it's also checked in the repo that we have. There's nothing GPUs on this example. It just shows the more fundamental things about Chapel. First of which is declaring an array and then writing it out and then incrementing elements of the array one by one or element-wise, but in parallel using a for loop and then writing it out again. I'm not going to compile everything here, but what we are trying to show here is the array declaration and the for loop that is a data parallel loop. And again, if you go to the repo that I was just pointing at, you can see pointers to documentation of array declaration and things like parallel loops and write-alens and things like that. So it points you to the right direction if you want to learn more about any of these concepts. So again, this is how you declare an array and operate on it in a data parallel way, but on a CPU. What comes next is how to do that on the GPU. And doing that on the GPU is a twofold thing. One, you have to declare the array on the GPU, and two, you have to do the operation on the GPU. So declaring an array on the GPU uses the on statement that we have in Chapel. So on statements have been with the language for since its beginning, and it's basically a statement that can allow you to move execution from one locale to another locale. And locale typically means a compute node, though it can be a socket, for example, or a sublocale could be a GPU. So locale is basically a unit of locality in Chapel that we use a lot. So here the on statement, this is not actually on statement, but it uses something similar to that. So this on is actually saying that the declaration that we have after it will have to be done on the target locale of this on. And here, what we are using is the here built-in Chapel that tells you the current locale that you're executing on. And GPUs is just an array of GPU sublocales in that locale, and we are just targeting the first one here because it's a zero-based array. So now this array R will be on the GPU. And if you do a side-by-side comparison with what we had before, so this was the array declaration that was on the CPU, and here this is the array declaration on the GPU. So the declaration is basically the same. You just, if you will decorate it so that it's a variable declaration that is on the GPU. And we write it out again. So here, this operation is again how we increment it one by one, but then again, this is still on the CPU. Even though R is on the GPU, we have to still tell Chapel to do the operation on the GPU. If you do it on the CPU, what Chapel will do is just it will copy elements one by one under the hood for you through the runtime, which will not be efficient in terms of performance, but it may be what you want in terms of the operation that you want to perform. What you want to do if you want to move it to a GPU is then use an on statement here. So this is again similar to what we had for variable declaration, but this time this is just on the for all loop, which is a data parallel loop. And now what we are doing is we are moving this data parallel operation to the GPU sublocale. And what will happen is the compiler will turn this for all loop into a kernel, and runtime will launch that kernel under the hood because you're executing on a GPU's sublocale. Any questions so far? Or any comments about font size or anything like that? All right, let's go to the next example on this repo. So I've been talking about this locale concept a lot. So again, it's a unit of locality. What we have here is a demonstration of locales being first-class citizens in Chapel. So what I mean by that is just like an int or a string or a real, locale is a type in Chapel. And that you don't have to use anything additional. It just comes with that locale type built in. And what we can do about this is you can declare your own locale variables, and those locale variables could be a GPU or CPU locale. It doesn't really matter. And this example is essentially the same code that we had before, but what it does is it has this line, which is the key line here, or maybe the first two lines. So let me start with the first one here, which is, again, has nothing to do with GPU programming in Chapel. This is a config const. So const is basically a constant variable. Is a constant value in Chapel. And if you decorate it with config, what happens is you will have a command line argument with this name. So since we have a config const named use GPU, when you compile this application, you can use -- use GPU flag and set it to true or false. And it will determine whether you want to use a GPU or not. And the way that we use that flag is only on this line. So here what I'm doing is I'm defining, or rather declaring, defining a locale variable, which I call a target locale. And I choose between here.gpu0, which is the first device on this node, or just the node itself, depending on this flag that we have. So what happens here is if you pass use GPU equals true, or if you just let it be the default, it will be the first device on this node. If not, it will be just the CPU itself. And if you look at the rest of the code, it's pretty much the same, but now my own statements use this target locale variable. And there's no other change in the implementation of the loop or the array declaration itself. So what will happen is now you have this one piece of code that you can run on a CPU or a GPU depending on a command line flag. And there's no like application level magic that you have to pull through here. All the magic is happening inside the compiler and the runtime, and it's all handled for you here. And this is how useful locale variables can be. I think I see a hand, maybe Michelle?
Yeah, so Engin, for a little bit more background for folks who may not know what a locale is, could you talk a little bit about the correspondence between a locale and a process and what this looks like, whether it's going to run on the CPU or on the GPU?
Yeah, that's a good question. So for GPUs, I specifically want to use the term sublocale because GPU sublocales are technically not full-blown locales. And what I mean by that is essentially the answer to your question. So typically in Chapel, a locale is a process. And in the most basic scenario, you run one process per compute node, and those processes are represented by locales. We have some recent efforts where you can opt in to running multiple locales per node. So for example, you can run two or one locale per socket if you have a dual socket system, in which case you will get a process per socket. So locales give you that kind of abstraction in general. What GPU sublocale is like from a programming language or a programming language standpoint, it's still a locale type, but they are not represented by processes. So they are just like they are basically properties of the tasks rather than processes. And what task is essentially, okay, I'm taking a long-winded approach here, but Chapel uses Q-threads for its tasking layer. So what happens is if you're running a process per node, for example, each core will be using a single, will be using a Q-thread, and we have a lot of control over these Q-threads. And what happens if you move things to a GPU sublocale is you essentially get a Q thread that knows that it's running on a GPU sublocale. And running on a GPU sublocale doesn't change anything except for array declarations and data parallel operations. So you can do a write ln on a GPU sublocale, for example. It will still be executed on the CPU. But if you are doing a data parallel operation or an array declaration, it will be satisfied through the host because the task that is running on that sublocale is aware that it is running on a GPU sublocale. Did I answer your question?
Okay, that was really helpful. Yeah.
Okay. Any other questions? While I could take a sip of water. All right. The rest of the examples from the previous demo are basically building on these concepts, but doing something more realistic. And I want to skip the third one, so I'll just jump to the fourth one, which is a little more complicated, but today's demo will basically build on top of this, so I wanted to show this. So what this code was from the previous demo is, again, building on the same idea of using a target locale. But what we have here is more realistic to more conventional or typical usage of a GPU, in which case, by that I mean you have data allocated on the CPU memory. It might be through some I/O or some initial preprocessing. Then you want to offload that data to the GPU, and GPU does a lot of like number crunching, and then puts the data back onto the CPU. So this kind of like data offload and bringing it back is kind of a typical GPU workflow. And this code is showing that. So what I have here is I have the CPU data array. And I'm moving the execution to my target locale, which is again determined by this use GPU flag. And then what happens inside the locale is I define another array, which I call GPU data, and I just set it to be CPU data. So this is a pretty intuitive variable declaration, I hope. But what happens here is the runtime determines that, okay, I'm executing on a GPU sublocale, so this array has to be allocated on the GPU memory. But then, oh wait, I'm initializing it with a CPU array. So what happens under the hood is this data will be moved in bulk from host memory to the device memory. So essentially, what happens under the hood, if you're familiar with CUDA, for example, this will be CUDA memcopy call that will be handled for you under the hood, or HIP memcopy if you are using HIP. So now we have our GPU array, and that is a copy of the CPU array. And what I do here is just some random math operation, which is basically I'm just setting each element on this data to the hyperbolic tangent of themselves, and I'm just summing up the absolute values of that. Kind of like an integral, but not quite. So there are a couple of key points here. First of all, I'm using the math module functions, tanh and abs, so they are coming from the math module. This is just a standard Chapel module. You can use the same functions on CPU as well. They just know what to do based on where they are running. And another interesting thing that is different than what I'm showing here, what I was showing before, is this part of the code, which is what we call a reduce intent. So what happens here is this is a data parallel loop. And what I do here is I'm just adding values on top of sum. So unless you tell something to the compiler or the runtime, this could be a racy situation, right? Because there's multiple threads trying to do the same operation, and you're adding values on top of sum. And in fact, if you drop this, compiler will complain that this is a race condition. So what we do here is we are just telling the compiler that I'm sum reducing the value sum. So what would happen is, even though this is a GPU kernel, the compiler will generate the right kernel and runtime will handle it in such a way that sum will be reduced using GPU functionality. And in fact, what will happen under the hood is we will call out two libraries called cub and hipcub, if you're familiar with those. So they are basically fundamental math-like operations. I don't know if math-like is the right term, like sorting, reductions, and things like that are in that library, cub or hipcub. So we'll be calling those. So the performance is expected to be near ideal, or whatever the vendors provide us through cub and hipcub, essentially. And then what happens at the end of the block is we just copy the data back, which again is, I'm hoping, a very intuitive line of code here. I'm just copying the data back. And the fact that one side of it is on the GPU and the other side is on the CPU does not matter. The runtime will handle it for you as efficiently as it can. And in fact, what will happen is a single CUDA memcopy call here. And that was the last example from before. Any questions so far? That was a long recap. All right. So what I will do next is I will build on top of this and have the same logic, but this time extend it to first multiple GPUs on a single locale. Then I will make it such that multiple GPUs are used concurrently instead of one by one. So this is just an additional small step. And then as the final step, I will use all the nodes and all the GPUs available. And if my session here is still active, in the end, I'm hoping to show you the execution on an actual supercomputer. I say this because what I will do is also something different. So right now, what I'm using is my MacBook, which doesn't have NVIDIA or AMD GPUs. So I configured my Chapel in CPU device mode. That's what we call it. So what happens in this mode is GPUs are essentially emulated, even though you're not running anything on the GPU. So this is a way for developers to use their own laptops, even if they don't have a proper GPU, to develop their applications, make them ready for GPU, debug them, and then run on the supercomputer or the cluster that they have once they are ready with the implementation. All right. So with that out of the way, let me copy the directory, and I will try to do everything live. Everything will work fine, right? All right. So let's work on that. And I'm just gonna make the name correct as well, just to avoid confusion. All right, so this is the code that we were seeing before. So what I mentioned is, again, using all the all the GPUs inside this locale. And we build everything on top of this target locale variable before, so I'm just gonna keep building on that. So instead of having this, I'm just gonna keep the previous version commented out for reference. So I still want to use the use GPU flag, but if you use GPU set, I want to use all the GPUs. And all the GPUs inside the locale that is called here, or where I'm executing right now, is essentially the GPUs array. So instead of just picking one, I just have to pick all the GPUs. So that side of it, the story is done. What will be problematic here is you want the same type of things on both branches of the if here. This is more about general programming practice. Like, this is not a compile time selection. This is an execution time selection. So you want to have the same type on both branches because of Chapel's strong typing. So now I have this locales, array of locales on this side. I need an array of locales here as well. So what I can do is I can just make this an array. So here, instead of just saying here, I'm just using an array literal with just one element in it, and that is here. So now, based on use GPU, it will be either array of GPUs. It could be just a single GPU if that's all you have, or it could be 8 GPUs, or it will be just an array of single locale that is here. So what I do next is I have this on statement that goes to a target locale, but now the target locale is not a scalar thing. It's just there's multiple things. Well, if you have multiple things, what you typically do is just you iterate over it. So I'm just going to iterate over this target locale. In fact, while we are here, let's just name it target locales. And let me comment this line out too. For lock in target locales. And now I'm iterating them, but for each one of them, I still want to have this on statement going to that specific locale. So what I do is do on lock. And do is not something special in Chapel, so I could very well write it like this. If I want to use curly braces, it's definitely a matter of style here. So this is pretty short for loop, so I'm just using a do here. It's all up to you. So here what I'm doing is I'm iterating over target locales and doing an on statement to each of these locales. But now the problem is we need to divvy up the work, because if I have multiple GPUs, I don't want all of them to do the same work. I want them to have chunks of the work, because that's how you get performance out of parallel execution, right? So what we need to do for that is to do some math, and we need to compute what part of the data we need to copy from the CPU here. And I want to keep the math simple. So what I will do is, instead of having a size n for the whole data, what I will just do is I will do n per locale here. So and with n per locale, what I'm trying to achieve here is that I want to make sure that no matter how many GPUs I have or how many nodes I have, I always have divisible amount of data, which is not the case in real life, but handling the math would be just too complicated for this demo. So I declared this, but now this is just per locale size. What I need to do is also an overall size that is n. So what I can do for that is relatively simple here. I will still define an n, and it would be the number of locales I have in this target locales array. So again, this is just a chapel array, and the way to get a size of a chapel array is, well, just do dot size on it. Sorry, it's not just this, but then times n per loc. So now with this, I have a divisible number of elements in my array, and then arrays there, and I do my for statement here. Well, okay, I went too far. So this is, again, a math adjustment that I will make. So this is not actually divisible, because there will be a 0 from minus n to n. So I will just keep things simpler here, and I will just do it 0 to n and non-inclusive to, again, make the math work. All right, so now my array is divisible. Ensure that, which is kind of a workaround for the demo, but hopefully a reasonable one. So what I will do here is we need to be able to find our start index and our last or like the final index that we need to copy from the CPU for each GPU that we are operating on. So what I will do here is I will just use range variables in Chapel. So range variables are here, for example, 0 to n non-inclusive and 0 to n non-inclusive. So these are, again, first class citizens in Chapel. So what I want to do is I will declare a my chunk variable. And what I want to do here is, so I'll define a range, and these are all zero-based indices. So I will use my GPU ID. This is, again, zero-based, so the first device will have ID 0. And then based on that, I will have to offset my index, start index by n per loc. And then I'll just want to grab n per loc elements from that. Let me go over this operation here again. So let's say you have two GPUs with 100 elements each. The first GPU will be ID 0, and this will be 0. So you will be grabbing 0 to 99, essentially. And then for the second GPU, this will be 1, and n per loc will be 100. So you will start from 100 and then pick 100 elements after that, which will end up in 199. So now we have my chunk range for each GPU. But what do I do with this? So what I do with this is, again, using a very expressive feature of Chapel, which is array slices. So you can slice arrays in Chapel, and you can use ranges for that. And that's exactly what we need here. So instead of copying full CPU data, I can just copy my chunk of it. Note that this is the same syntax as just indexing an array, but this time I'm just passing a range. I copy only a chunk of it, and at the end, I only copy a chunk of it back. So adjust both ends of the story. And that's pretty much it. So this slice, again, will be handled as efficiently as possible in the runtime. There will be some, of course, like, is this a slice kind of a check and things like that happening on the runtime. But eventually, what will it boil down to is a single CUDA memcopy or heap memcopy call, depending on the hardware that you're using. And I believe that's it. So let's see if we can compile this. There must be some syntax errors that I made. Right, and reference before. Yep. Let's do it here. That makes sense. So use before defined error was the only one probably I got. Oh, sorry. Let me. Sorry. Let me compile this again. I was just testing multinode before I joined the call, so that was coming from the multinode runs. I don't want to go there right now, but we will get there. So I compiled it, and now let's run it. And now we get the sum on the GPU and sum on the CPU. And this is what is printing out, essentially. So what I mentioned first, before I started on this, is I'm using my Mac, so this is just emulated GPU. A good benefit of that is essentially you can just ask for any number of GPUs you like, and the runtime will just obey as long as your CPU can handle it. And the way to do that is using an environment variable that might be a little bit mouthful, but Chapel RT stands for runtime non-GPUs per locale. So if you set this to any number, let's just set it to 2, you will get now 2 GPUs. So you are getting one sum from one GPU, another sum from another GPU, and then you end up getting the sum of the 2 from the CPU. And we can maybe reduce n per lock by half to see if we are going to get the same result. This is 4299 something, and I believe that was something that the same value that we are getting. So essentially, I just reduced the number of elements per locale by half so that I'm operating on the same amount of data and still getting the same result as single GPU. And what's good about this is like you can get crazy with it. Like, I don't know if this will work, but like I'm now using 17 GPUs on a node, which I don't think it ever exists, but you can experiment. Any questions with this one? So I'm gonna unset this because that's not how I want to use it, but I'm going to use it like this, like before my command, I'm just gonna set it so that we can see the number of GPUs that we are using for each run. So here again, we are using 2 GPUs, which is a more reasonable number here. Okay, so this was how to use multiple GPUs. But if you run it repeatedly, you will see that the results are always printed out in the same order. And that is because I used a for loop here. So if you're not familiar with Chapel's parallel constructs or Chapel in general, it doesn't try to do auto-parallelization for you. So as the user, you have to use parallel constructs to get parallelism. And for loop in Chapel is sequential. So it will never get parallelized on its own. So you have to use something parallel here. And that will be my next step. So let me create a new example. And we will go from there. Okay, so this was my code. And again, it was just running sequentially. And what I want here on this line is, instead of running each iteration of this loop sequentially, I want each iteration to be run in parallel. And the loop flavor for that in Chapel is co-for-all. So if you have a co-for-all loop, what will happen is there will be nothing smart with co-for-all. Every single iteration of the loop will turn into a task that can run in parallel, which is powerful, but it's also a double-edged sword. Like, it's a common mistake to run a co-for-all over 1 million elements, for example, which will result in 1 million tasks to be created, which I'm almost certain will crash your runtime, because that will be just too much memory and too much context switching. But if you have a small number of iterations, which is hopefully the case here, like number of GPUs will never be that high within that node, then co-for-all is what you want. So let's go to that directory and let's compile this application this time. And let's see the outputs. Looks similar. Let's do the GPUs per locale to something a little high. And as you can see, the order of the output changes every time, but we are getting the same result again and again. So very simple change 4 to co-for-all, and you'll get, can you still hear me? I did something and.
We can still hear you.
Yeah, we can.
Perfect, thanks. My Teams window just disappeared, that's why I was just checking. And by just changing the loop flavor from for to co-for-all, now I have a parallel execution. Another loop flavor here is for all, which will also be parallel, but it's a little bit more, it's definitely a way more common type of a loop in Chapel. And what for all does is it will determine the parallelism based on the thing that is iterating on. So the impact here will be the same. It will still be parallel because Chapel arrays are iterated in parallel if you're using them in a for all. But then again, the amount of parallelism is completely determined by what you're iterating. So if you're iterating a large array or a large domain or a large range, you should be iterating it with for all. And ranges, arrays, and domains know how to use number of cores efficiently, as opposed to co-for-all, where the loop will just blindly create number of tasks equals to number of iterations. Any questions here? As I mentioned in the beginning, this was a quick step to show different kinds of loops in Chapel. If you are all good, the next step will be to use multiple nodes that have multiple GPUs in them. And for that, I will still be using my MacBook, which is obviously a single node system. But just like the way of emulating multiple GPUs, there's a way of emulating multiple nodes in Chapel as well. And I'm going to be using that. Multi-GPU. Oh, I shouldn't be doing this live, so I misnamed things, but that's okay. So this will be, I'm just going to name it multiloc. Right. So this is what we were working with, and let me get rid of these comments to make the code easier to digest. Okay, so far what we have done is to use this target locales variable to set basically what kind of locales we want to iterate on. But Chapel is a high-level language that has a lot of features that kind of that doesn't exist in languages like C. And one of those features is iterators, which is more familiar with languages like Python. So what I will do here is, instead of using target locales variable, I will define my target locales iterator. And based on the use GPU flag, it will just iterate over all the GPUs that you have available to you, or just all the CPUs that you have available to you. So defining an iterator is similar to defining a function in Chapel. Instead of proc, you just use iter. So this is my iterator declaration. So what I want to do is I want to iterate over all the locales or all the nodes that I have without thinking about GPUs for a second. And for that, Chapel has this locales predefined built-in array, if you will, which is just a Chapel array. So you can iterate over this built-in array and it will just yield locales at each iteration. So I want to iterate over each locale. And if I'm using GPUs, and in fact, let's change this flag too to make it more read nicely. So if I'm using GPUs, I also want to iterate over GPUs in that particular locale. And if I'm iterating GPUs, what I want to do is I will just return or yield those GPUs to the loop that will be using this iterator. And the keyword for that is yield. So I will just yield the GPU. And if I'm not using GPUs, I will just yield the locale. And that should be it. So this is my target locales iterator. This looks a little bit too much braces, so I'm just going to use single liner, one-liner syntax to keep things nicer. And this is again all a matter of style. There we go. So now this target locales iterator will just yield a bunch of GPUs, sublocales, or just top-level locales that just are CPUs, depending on the use GPUs flag that you use. So now we don't need this. Let me comment this out. Trying to see what do we need to change here. So target locale size will not work. You cannot query the size of an iterator. It's not supported yet, so we need to work on that. So let's try to fix that. So we need to compute the number of nodes we have. So for that, what I will do is first I will compute number of GPUs we have per node. So and GPUs per locale, and I'll just pick the size of the array of the GPUs array that is here. So here, this assumes that each node has the same number of GPUs, but that's a typical assumption in Chapel and many other similar languages in which we just assume that nodes are homogeneous, like not internally, but each node has the same architecture. So we are just building on top of that assumption, and we are just setting number of GPUs per locale here. And then what we will do is define another constant, let's say num target locks. This will be if I'm using GPUs equal to num locales, which is another predefined thing for you, but you can also do locales.size, which is again locales is an array, times n GPUs per locale. And if not, let's just mix and match built-ins. All right, so now if I'm using GPUs, I don't like that. I don't like inconsistency. So if I'm using GPUs, I'm just computing number of GPUs here. And if I'm not using GPUs, I'm just using nodes. So this is my number of target locales. And now I can adjust this. All right. And with that out of the way, let's see where target locales are used. Oh, OK. So next up is my loop. The only little change that we need to do here is syntactical. So this is an iterator that you need to call if you want to iterate it. So this has to be a call. So now I think this should be ready to go. Let me see if it's compilable right away or if I made some mistakes. All right, this compiled. Let's see. Oh, I didn't. OK, I need to set my chapel. So so the chapel that I was using is not built for multi-node execution. I actually have multiple runtimes built, so I need to pick the runtime with GasNet. In order for you to be able to use our GasNet COM layer in this setting, what you need to do is just set chapel comp to gasnet, and then you export gasnet spawn fn to L. And in some systems, I believe it's the gasnet master IP environment variable. You can find more information on portable UDP layer documentation in the chapel documentation. So now that I set my environment variable gasnet, chapel comp to gasnet, I believe I did. Okay, perfect. So now I am using a multi-node chapel, and let's see if I can compile this again. Now this time around, when I run this, I will have to pass, ignore the linker warning, please. Again, this is not my typical work setup. I don't know what that is about. I need to figure that out myself. So when you run the executable this time, it will ask for you to give a number of locales. So now this is a multi-locale build, and I can run with 2 locales, and then I can set my number of GPUs per locale to 4, and it will compute the value. So now let's see, how can we confirm this? Okay, let's do this. I'm gonna use 1 GPU and 1 locale only, but I'm gonna set number of, what was our variable? Now n per lock. Oops, what did I do? N per lock to, let's say, 1600. So this is what I get with 1600 elements per locale. So now what I will do next is I'll just use 100 elements per locale, but I'm gonna use 2 locales and 8 GPUs to make the math add up. Oh, okay, there was a mistake here. Yeah, sum is off because there is a mistake, and I think I know what it is. I'm glad that we run this. Anybody want to take a guess as to what the issue is? That's my excuse to take a sip. So the issue is coming from this line here. So what we do here is, this is actually a remnant from an earlier iteration where we were just assuming that we are iterating over multiple GPUs in the same node, and that's it. But now, in order for us to compute my chunk correctly, we need to understand where we sit in the big picture. Like, there are multiple nodes, and GPU IDs are assigned per node only. So if you have 4 GPUs per node, it will be 0 to 3 on each node. So there will be a bunch of log.gpu IDs that are 0. So what's happening here is multiple GPUs on different nodes are operating on the same data, actually, which is not what we want. So we need to handle that somehow, and we need to define maybe my global ID of sorts. And how do we compute that is, for each locale that we have, we actually have an ID. So that's the parent locale's ID, if you will. So that's a top level thing. And then for each locale, we actually know how many GPUs we have, right? And that's the variable that we have that we named n GPUs per locale. And then once we set this offset, and then we can just increment by log GPU ID. So let me expand on what's happening here, and let me put some spaces. So let's say you have, what was our example? 2 nodes with 4 GPUs. Let's say 2 nodes with 8 GPUs. So first node will have locale ID 0. So this will be all 0. And then GPUs will have IDs, global IDs 0 to 7, because they will have GPU ID 0 to 7 here. Then for the second node, loc ID will be 1. So this multiplication will be 8. And then the GPUs will get global IDs from 8 to 15, if my math is right. So now we corrected the math, and now we can use that ID that we computed here to use the correct chunk. Compile it again, and let's run it again. I forgot what the value was, so I'm just gonna use 1600 again, and 1, and 1, so 693,669, 693,669. So now this is the evidence that using one single GPU versus 18 GPUs across 2 nodes generates the same result, but arguably much faster. And this is actually a good demonstration that was not scripted at all, that the value of being able to use multiple node settings and multiple GPU settings on a system that doesn't even have a GPU, it's just a single laptop. So instead of like trying to debug these kind of math errors, which are inevitable, instead of trying to debug them on a supercomputer that would be really hard to get cycles on and whatnot, you will have to wait in the queue and things like that. You can just be, comfortably addressing these kind of issues on your own setup on your own laptop.